Okay, now that recording is up and should be up soon. All right, today we will switch gear a little bit. Welcome to the last portion of the class. Um, and everything up to now, up to lecture number 9, will go for a part of the midterm quiz. I need to call it quiz, by the way, which will happen in 2 weeks. In 2 weeks. The topic cover for the midterm is everything up to lecture 9. Everything up to lecture 9. It does not include this lecture. This is everything we are going to talk about from this lecture onward goes to the final. And here's the logistic. Quiz will be released around 9 a.m. on Tuesday, October 26th. Why so late in the semester? Surprise holiday. I did not know next Thursday is a holiday. That was the original date for the midterm. And now we have to push it because of the this government declared additional holiday. You have until 11:59 p.m. on Friday to submit. Is that enough time? So let me ask you this first question because this is the month that there's so many things going on. Um, the country would start opening up. There's so many holidays. I don't know what's your plan, and I don't know what about the other class plan. So I want to give everyone their room to pick the time to work on the exam. The exam is not designed to take 3.5 days for sure. It's not designed to take 3.5 days. It's designed to take 2 hours. Make sure you allocate your time so that you can read the exam. Did you get the feedback from the quiz from the TA? We will, so these typically I would grade on a paper, but once we come to the online format, I've been doing a really bad job about like giving feedback. This semester, because we have TAs and they're awesome, I will try my best to basically do two things. Basically, we'll do the typical thing is I'll go over the exam, right? And then after we go over the exam, we will give the feedback on the exam for all of you through, well, I'll find a method to do that. I'll need to find a method to do that. My suggestion right now is I'll put that in the comment box on your submission because the exam will be posted on Canvas. You're going to submit it on Canvas and make sure, well, make sure you don't copy your friend's code and things like that. Oh, yes. I get feedback from the TAs. I'll give the draft to you. I mean, not to you, to the TA, and I'll ask them, is this will this roughly take 2 hours? If they say yes, I'll believe their word. Right? We have 5 TAs. I I I think if it's too hard, you can mostly blame me for sure, right? Mostly blame me. But if your TA are trolling and say, "Hey, it's easy," um, it might be longer. And you have, yeah, 3.5 days to kind of pick out your 2 hours to work on the quiz. I mean, you can spend the entire 4 days on that too, right? You might be asking, why do I give everyone so much time? First of all, I don't want to make sure you all will have the time constraint because everything is online, open book, right? What I want to make sure is if you want to learn, and if somehow it's like, hey, oh, I screwed up, I need to learn this topic a little bit more, spend time to make sure you know how to work on it. Because I think the important part from taking any class, right? The most important part is whether you learn or not. I don't want to pressure you into asking your friends like, oh, what's the solution? I want to minimize plagiarism. I want to minimize working together on the exam. Please don't work together on the exam. All right, I'm gonna ban everyone from working together on the exam. It has to come from you. This is where we test your knowledge, right? But There are going to be a lot of time for you to look through the questions. There'll be a lot of time for you to manage your own time. So this way, most, well, I guess the grade that you get on the exam will be hopefully reflecting what you know. All right. There might be some more open-end questions, or maybe some of the more like, okay, these are the answer. You have to get it correctly kind of questions. Um, it it should take 1 hour for the TA and me to do, and in theory 2 or maybe 3 for you guys. And I know what happened every single semester because they'll tell me I lied. Not my intention to lie. I definitely try to hold back, but sometimes when I have a good question, like, oh, I want this too. I'll try to make sure the amount of hours they have to put into the exam is within between 2 to 3. All right. My recommendation, once the exam is posted, look through them and gauge how long do you have to spend to work on these questions, because you would be the best judge of how long you would have to take to finish the exam. We will do a review session on Monday, October 25th. I think this is no longer the holiday. I think the government moved the holiday on the 25th back to 22nd. Uh, Likely between 4 to 6, because the first session told me that 2 to 4 is bad. Any comments about this slot? Does it work for you, 4 to 6? You have class from 4 to 6. Okay, no live. There will be a recording. There will be a recording. Will there be class on Thursday? Yes, there'll be class on Thursday. We will cover things for the final. And it might sound a little bit weird that the period you can work on the exam can span over like one more, like actually 2 classes. The first class on the 26th between, I guess, noon to 4 will be basically for the exam Q&A. You can join the class and ask the question about the exam. There's not going to be any new material covered on that day. The only thing we'll do is I'll have the WebEx open. I'll answer the questions about the exam. On Thursday, we will have an actual class. Okay. All right, everyone clear on this? Well, yes and no. I mean, you're giving me an idea about what I can do. So yes, it can have the bash script problem. I mean, look at the topic we cover, right? This is gonna cover certain things. Um, yeah, I probably don't have a lot of room on like things I can ask on the exam. It's gonna kind of, yeah. I know that you might hit bash script. I will take that information. Thank you. Joking, but yeah. So I'll make sure that it correctly kind of tests whether you know or not. And because it's open book, I mean, you can actually try on your computer, right? So I'll take that as a part of the information as well, because everything I'm gonna ask, you can definitely test it on your computer. I have to remember that when I make the exam. So be aware that this is open book, open internet, open everything. You have even time to go over material kind of exam, right? So I want to make sure you understand the fundamental concept, basically. All right, any questions before we go through the content? All right, so let's begin the class and talk about how do I represent data. And anyone want to recap on how do I represent decimal number to binary? So are we all pretty comfortable with that? At least you know a method how to do that. Or should I cover that? So what's number, I don't know, 17 in binary? How do I convert 17 to binary? One method, drinking coffee, and eventually I'll know what I'm doing. Yes, 10001, right? So how do you do that? How do you do that? Can someone tell me how do you come up with that binary number? Calculator, right? Well, calculator. Anyone use Google? Yes, thank you, Mario. So the other method is you can break this down, right, to number that consists of the factor of 2 to the n. In this case, 17 is 16 plus 1. 16 plus 1 is basically 1 multiplied by 2 to the 4, right? Plus 0 multiplied by 2 to the 3, plus 0 multiplied by 2 to the 2, plus 0 multiplied by 2 to the 1, plus 1 multiplied by 2 to the 0. 10001. 10001. So that's the number 17. This is essentially, if you think about it, if you have a number in a like let's say it's a decimal format, 1, 2, 3, 4, 5, right? The way you think is the same thing. You factor out, right? But it is a decimal number. So what do I change? How do I tell? How do I factor such that it has the same format as this, like 1 multiplied by 2 to the 4, 0 multiplied by 2 to the 3? The first thing I had to change is these are decimal, so you have multiply by 10 to the 4. So in this case, 1 multiplied by 10 to the 4, plus 2 multiplied by 10 to the 3, plus 3 multiplied by 10 to the 2, plus 4 multiplied by 10 to the 1, right? Plus 5 multiplied by 10 to the 0. That's why the binary versus decimal versus hexadecimal number, the thing that gets changed is the base. These are the base. The base can be, if it's binary, the base is going to be 2 to the n. The digit that goes into, the digit that go into this number, right, would be multiplied to the base. So what's the number 1100 in decimal number? So it is binary. When I do B and then dash, it means that these are binary numbers. So how do I write this in decimal? Right? It's 12. So as you use this a lot, to be honest, you're gonna use this more and more. If you go into things like computer system, you might have to convert binary to hexadecimal, hexadecimal back to binary. You basically you get used to this. But one of the most common thing you have to do for computer science is the conversion between hexadecimal number and binary number. So let's say I have a binary number, any random binary number. So can someone give me a random, maybe more than 10 bits long binary number? Because I want to tell you a good trick to convert that to hexadecimal number. All right, thank you. So it's 1001 or 111011. So if I ask you This is a binary number. What's the hexadecimal number of this? What do you do? What do you do? Hope that there's a library to cover it. What else? What else can we do? That's one thing we can do for sure. But if you think about it, I mean, I can just do printf %x actually. %x would print in binary. Because remember, everything is just a value. A value in binary would have the same value but different representation in hexadecimal, right? I mean, what else can we do? Anyone would do something differently. I mean, what would you do to convert this to a hexadecimal number? Segment this. Yes. How? You can segment this for sure, but how would you segment this? So the trick that you can do, right, is to segment this into section 4 number each, 4 digit each. And then what you can do is for each of these segment, convert that to a hexadecimal. So what's 1011 in hexadecimal? It's 11 actually. 1011 is 11. Yeah. 1011 is 11. 11 in hexadecimal is what? 10 is A, 11 is B. Again, 1011 B, 100, what's that number? 4, right? So in hexadecimal, whenever I write 0x in the beginning, in the front, these are hexadecimal number. So it's 4BB, right? Why can I segment this into 4 digits? Anyone want to guess why is it working? Yes, it is. Within this 4 digit, you can represent the number from 0 to 15, right? 0 is 0, 0, 0, 0. 1 is 0, 0, 0, 1. 2 is 0, 0, 1, 0. 15 is 1, 1, 1, 1. This is the exact same representation of each digit in hexadecimal. So if I have a number in hexadecimal, beef, let's actually make it longer. Because why not? This is one of the common hex number that you're gonna see in multiple textbook and lectures. 0x dead beef. How can I convert this to binary? I would do one by one. What's F? Yep, 1111, right? E is going to be 1110. Again, E is 1110. B is what? 1011, because you can see it from here. B is 1011. D is going to be E minus 1, so it's going to be 1101, right? A is 1010. E again is 1110, and D is 1101. So this whole thing equal to 0x dead beef. This whole long bit pattern, right? So this is basically a quick recap on how you can convert from binary to hexadecimal and hexadecimal back to binary. We actually would do this more. Oh, hexadecimal to decimal is a pain. So you would do you would in this case would do what's D? D is 30, oh my bad. 13 times 16 to the what? 0, 1, 2, 3, 4, 5, 6, 7 plus 14 multiplied by 16 to the 6 plus what is A? 10 multiplied by 16 to the 5 plus 13 multiplied by 16 to the 4 plus what's b? B is the 11 multiplied by 16 to the 3 plus 14 multiplied by 16 to the 2 plus 14 multiplied by 16 to the 2 to the 1 plus 15. There's no easy way around this except for and why do we not care so much about binary to hexadecimal to decimal? Is we use it actually less. We use binary to hex and hex to binary more often in computer. Why is that the case? Because of this reason. How can I talk to the computer? How can I talk to the computer? Before we begin about that question, we need to ask, I'll need to ask you, when you buy a computer, right? When you buy a computer and I want to read data from your computer, how do I represent those data? How do I represent a program? How do I represent the data inside the program? We use binary. Anyone wondering why binary in particular? If you're wondering, anyone want to take a guess? Why do we use binary? Exactly. It's just a yes and no, right? Because a lot of components in the computer can represent on and off, right? On and off is 1 and 0. In particular, when you have electrical signal, what you read from them is actually a voltage value, right? So let's say you have a time here, voltage here. One thing you can do is, let's say you look at the memory. For example, if you look at the memory, the voltage can range from 1.5 volts to 0 to 1.5. So how am I going to tell which one is the number 1, which one is the number 0? What can I do? I read the voltage. And how can I figure out, okay, that's a 1 and that's a 0. Well, maximum is 1.5, right? So I will have some threshold. Let's say if it's below this threshold, this is basically, if it's higher, it's a 1. If it's lower, it's a 0. So over here, this signal over time can mean 1, 0, 1, 0, 0, 1, right? So in this way, with the clock, remember the clock cycle of your CPU, like your CPU clock that can clock to like 3.4 gigahertz, 3.6 gigahertz. So that's the speed of your clock, and that's the speed of how fast you can change this thing around. When you see 1, it means that that signal is a binary 1, and you can combine them to actually represent a number. Right? So that's how you can represent number in a computer using electrical circuits, right? Voltage in particular. So the idea is, well, how do you program? Yes, this is a great question. There's a question to say, is quantum computer different in binary sense? If you talk about quantum computer, right, you might have heard about this terminology called qubit or quantum bit. Anyone heard about this terminology, quantum bit? So a digital bit, right, is kind of like 1 or 0. It can be one of the two. And yes, it has to do with superposition. Basically, if you look at a quantum physics, right, one thing you can, oh, I guess the elements of quantum physics is you don't guarantee that when you read, you're gonna get a 1, or you read the bit, you're gonna get a 0. With qubit, right? With qubit, there's a probability involved to read from the bit value, and it can be the position of the state between 0 and 1. So this kind of means, right? What it means is now one quantum bit would pack, you can pack more information per bit rather than just one singular ones or zero. It can be one, it can be zero. When you read from it, it's guaranteed in DRAM, for example, our computer, digital computer, if you read a one, it is going to be one. In quantum computer, that one bit can actually kind of it's in a quantum state. I'm not sure how what's the easiest way to explain this, but exactly. There's a kind of like infinite amount of information you can store in that one bit. So in that case, what are the main problem with quantum computer? Anyone want to take a guess? Like, what will be the case about quantum computer and why it's hard to build? Well, how are you going to read them? Right? How do you measure? That's the first question. How are you going to deal with noises? Because when things can kind of shift around, right? The state can change within the same bit. How can you tell that's not a noise? How can you tell that's not the noise of like the way you measure things or the noise between coupling of two quantum bits because they are close to each other, so they impact each other. There's a correlation of how you store data in one bit and it costs the state of the next bit, right? So these are different trade-off, and these are the difference between problems in digital computing versus quantum computing, right? There's quite a lot of people, especially physicists, who say that, hey, this is basically the next big thing, right? Is it so the question is that why they put in the code temperature so molecule won't create noise? Probably one of the reason. Probably one of the reasons. There's also other techniques from computer science that can be used to kind of like basically read it and assume there's noise. And we will make sure it's reliable enough. It's reliable enough that, hey, the data is going to be correct anyway. These are techniques typically called error correction. We assume things might have error, but we'll correct it. Uh, that is a little bit too much physics for my brain. Sorry. I'm not sure if that's involved or related to the quantum computing, right? Yes, yes. I think it depends on your observation at in any given time. So, I mean, since I go on this side topics anyway, yeah, I guess Schrodinger cat. Yeah. So I mean, since I'm going over this like side topics anyway, and it's a great topic, right? Uh, it's a new paradigm that can potentially solve many algorithms that was believed to be NP complete. Anyone know about what NP complete mean? I actually forgot that this is the slot for algorithm class, right? It's a famous problem in algorithm, which is P equals NP. Is it possible to convert non-polynomial algorithm? Basically, it's a algorithm is the way you write the program to solve problems, right? Non-polynomial means that let's say the input size is n, the time and the complexity that it's actually taking to solve this question is exponentially bigger based on n, based on the input. So as it grows bigger, it's an exponential growth in time. Polynomial is polynomial growth like n to the 2, n to the 3, Exponential growth is 2 to the n, 3 to the n. So what's the downside of non-polynomial algorithm? The downside is when n is big, it will take forever. It takes forever. So there's many algorithms that would try to approximate non-polynomial using polynomial time. When we apply certain assumption, we can make the problem nicer, and we will basically come up with the polynomial algorithm for that, right? To make sure the program is fast. Yeah, like the businessman, traveling businessman problem. That's one of the non-polynomial problem, right? And then quantum computer has been kind of shown that, hey, for the problem that are in the non-polynomial class, you can solve that in polynomial time in quantum computing. So what does it mean? It means that some of the problems that are known to be slow can be faster in quantum computer. Many people say, hey, that's a new way to like that's going to be the next big thing that would replace any digital computer. Would you be able to brute force everything then? Yes and no, right? Yes and no. Let's think about multiple cryptography algorithm that make sure that you cannot crack the code, right? You have a large number representing secret code, and you make sure that the computer within the lifespan of multiple human, right? Not just one generation, multiple generation of human, there's no way a brute force algorithm can crack the code. So that's actually applies to a lot of concept behind security and how you can provide guarantee. People who work on quantum algorithm have shown through some micro benchmarking that it's possible to crack that using polynomial time in quantum computer. So that's more likely that algorithm in security might have to change a little bit based on that assumption. You might have heard about, hey, quantum computer would replace your computer. My take on that, impossible, right? Because there's many things involved with normal day-to-day computer. I mean, if you are trying to program something in polynomial time already, why do you have to pay more to buy a quantum computer? Right? Why don't you just run it on a CPU? Why don't you run it on a GPU? My take on it is certain questions run best on quantum computer, certain questions run based on the GPU, certain questions run best on the CPU. There are pros and cons. There are trade-offs for every type of computer. And the more we have, the better, right? For the human being, right? The more we have is definitely better. But it's not like, oh, well, hey, this is going to be the better technology all the time. That depends. All right. Any other questions about quantum computing so that we clear it up and come back to the material for the class? So, in short, they're actually awesome, but the technology is like right now is in the research phase. We are still trying to build how to program them. We're trying to build how to best compile them, compile the program. For this, right? I think for the theory part of how this works, physicists, for the algorithm part, probably computer scientists who work on algorithm, in particular quantum algorithm, they might have to take some more physics class. For the hardware side and integration into system, let me know. I know I have some additional like readings that you can do. There's also like open class that you can take from like IBM, for example, that you can kind of like take a quick dive into what was called quantum computing. So I think it you have to ask the people that work on quantum computer. When I talk to physicists, for example, they don't know a lot about computer science. So they are great at asking the physics questions that have to do with the machine. right? That has to do with a machine. Then, if you can think about the algorithm part, right? At the algorithm part, then talk to the computer scientists that work on quantum computing. They would be great to kind of like learn more about the how do I use it. Let's assume I have this machine. How do I use them? All right. So hopefully that addressed your question a little bit. All right. So let's come back to the content of this class, right? Come back to the normal realm, not the quantum realm, and have binary number. So our idea is if you want to represent data or program, how do you write your program? What do you program in? Do you write binary or do you write something else? It's a human readable code, right? It's actually a bunch of English words and sometimes English non-words, alphabets and number. But if you think about it, computer only knows 0 and 1. So you can use this binary format to represent both your program. You learn about this when we talk about assembly. You use binary to represent your program. We also can use binary to represent your data. So you can use this as an interface between assembly code and computer. So to represent the data, right, everything the program do involves data. Data as an input, data as an output. Any questions so far? Basically, everything you do with the program involves the data. Things would come in a binary format. Things would go out as a binary format. The program convert that into a human readable format. And the way this data are stored, you have to be organizing this data in the main memory. So program will have its own view of address location. Remember our old friend pointer, right? The pointer would point to an address. And we'll talk about this virtual address concept, but this pointer are virtual address. We'll learn how that's done and how do we actually convert that to physical address that points to the location in DRAM. And when the program is executed, the compiler and runtime would control these memory locations. They determine where the data being stored. They provide the mapping between virtual and physical address. And now that we have the address and we have the concepts of data, right? Data that are in binary format. What I have to tell you next is I have binary ones and zero, and how do I attach meaning to them? And that's a concept of a word. So what is a word in English? What does it do? What does a word mean? It's a string of character, right? That holds certain meaning. If I say, yeah, it's a collection of character. Yes, exactly, right? It's a bunch of character that means something. And when I say something, I don't say a character, I would say one word. Cat, right? What does cat mean? It's an animal, right? That would walk around and like to knock over stuff, right? Uh, and there's the meaning behind each word. But when I told you this word, I'm not gonna say CAT, right? I will say cat. I'll bundle them together and send it to you. So the computer would do the same thing, right? You have a bunch of data, a bunch of binary bundled together, and you send a word. It's a unit of data. It's a unit of data that you will send and receive. So you might have heard about these 64-bit machines or 32-bit machines, right? in the current modern day machine that use 64-bit architecture, 64-bit means how many bytes? Each byte has 8 bits. So a 64-bit machine has 8 bytes. It means that one word would consist of 8 bytes. It's the unit in which the hardware would use to transfer data over together as a unit. They would transfer 8 bytes, they would transfer a word, send the word over, right, from one place to another. They are typically done as a unit. So that's a word. That's a word in computer science. Different architecture can support finer or coarser data size. For example, GPU can support half word, which allow you to put together 2 pieces of data and send it once. The memory would actually consist of multiple words and send a bunch of these words at once, right? Any question about data word? Any questions about the data word? It's just a unit of data, to be honest. It's a unit of binary sequence that together means something to the computer. So let's say we have that representation of a data word in mind, right? The next thing is, well, recall pointers, right? Pointers. Pointer is what? What does pointer store? It store the address. Let's say store PTR. This store the address. The address point to the exact byte location, right? So memory address will specify the exact byte location. An address can point basically when you have this exact byte, that location is the first byte of that word. Basically, the address you see is the first byte of that word. So access to the next word would move the address by the size of the word. So if it's a 32-bit machine, it will move by 4. If it's a 64-bit machine, which means you have 8 bytes per word, it will move by 8. And in C, you can use %p and %x to represent and print, basically to print out pointer and hex number. All right, so last thing before we kind of wrap up memory mapping, big versus little endian. Why is this important? Most of the time, you'd never have to care about this unless you're going down and have to modify the machine code or the kernel code, or have to deal with embedded processor. Or microcontroller, where data can stream in and out. You need to make sure when I refer to a word, where is the first byte of that word? So bytes in the word, again, right? Because let's say we have a 32-bit machine. 32-bit machine contains 4 bytes. Bytes in the word can be ordered differently based on architecture. I'm gonna explain the definition first. Right, let's say this is your data. 0x 1 2 3 4 5 6 7 8. Let's say this is your data. When I say least significant bits, which one is that? Which bit is the least significant bits of these data? 8, right? The rightmost is the least significant. And if you want to memorize why, least significant, it basically means that if I flip that bit, it has the least impact on the value, right? So if I flip this bit from 78 to 77, I flip it from 78 to 77, what's the difference in the value? Well, 1, right? If you subtract the two number, you're gonna get the value 1. You flip one bit, right? And the value difference is 1. That's why when you change these bits, the value doesn't change a lot. The most significant bit is at the top half here. If I flip, for example, from 1, 2, 3, 5, 6, 7, 8 to 0x 0, 2, 3, 4, 5, 6, 7, 8, I only flip one bit, change from 1 to 0. What's the difference in the value between the two numbers? You can say a lot, right? But you can see that now I flip one bit, but the value changed a lot. So that's why we call this most significant bits. So in a big Endian machine, least significant bytes is at the highest address. Little Endian, least significant bytes is at the lowest address. And different machine use different representation. Older version of x86 or ARM, the older version of ARM use Little Endian. Network protocol use Big Endian. Newer version of your processor, like IA64, this is the Intel Itanium processor. ARM, Alpha, and MIPS can support both formats. Yay, confusion. So let's assume I have a data. My data is 0x1234567 and the address of x is 0x10. Because these are 4 bytes data, x would cover the range from address 10, 11, 12, and 13, right? 10, 11, 12, and 13. If I have this assumption, let's break down what gets stored at each byte. Again, how many bytes is x? How big is x? How many bytes is in x? I mean, this is a hexadecimal number. The way you can remember how many bytes is this is two alphabet here is 1 byte. 1 byte, 1 byte, 1 byte, and 1 byte, right? So over here, there are 4 bytes. This whole thing, x is 4 bytes long. So the address of x, which point to 10, will occupy 10, 11, 12, and 13. Little Endian machine, again, Little Endian, significant bytes, lowest address. Lowest address here is 10. So least significant byte is 7, 8. You put 7, 8 at 10, 5, 6 at 11, 3, 4 at 12, and 1, 2 at the byte 13. Big Endian machine or network protocol would put the least significant bytes at the highest address. Least significant bytes here 7, 8, here 5, 6, 3, 4, 1, 2. That's all. Any questions about the big versus little Endian? Because if there's no more question, let's transition to the next topic and talk about data type and data representation. Unless, all right, clear your mind. Should we do a 5 minutes break before we resume? All right, let's do a quick 5 minutes break. We'll resume at 3:05. Oh, that's a different. Yay, you were right. Actually, it's data conversion that's buggy. And we'll talk about that. So the Apollo, the reason why things went wrong for some of the launch, uh, definitely this is a great scientific material and great engineering material. I would encourage you to check it out because it's the one thing I love about how these engineer does thing, especially people at NASA, is they document everything. So you have the detail, not just hey, a thing exploded, but they want to know the reason why So the next time you do it, we don't have the same problem, right? Uh, Repeating the same mistake again over and over is not their strategy, definitely. And how you troubleshoot is you need to learn from your mistake. You need to learn from your mistake. And the reason why I show the video again, because these days there's so many things, to be honest, that are being controlled by software. So when you write a program, it can actually impact people's life, right? So when you have bugs in your program, it can cause some catastrophic sequence of things that can kill people. And you don't want to be that person that, hey, I write that code that just kill people. Anyone heard about the Boeing 737 Max incident? There was a couple of years ago that ended up basically all airlines have to ground that plane. Anyone that has Boeing 737 Max 8 has to be ground. I think it's Max 8, but I think that's a model name. What happened is there's a software that if certain thing happen, it would kind of basically override the pilot input and force the plane to dive into on Earth, like basically dive to the surface of the Earth, killing everyone. Two planes crash. Hundreds, like I think 300, close to 400 people die from those two incidents combined, right? You don't want to be that engineer who write that piece of code. There are going to be things like self-driving car. There will be many awesome technology. Make sure you write safe code, right? And I'm sorry that I kind of laugh about toward the end of that sentence, but buggy code are really common. Like you suggest here, like Windows updates sometimes introducing new bugs, right? We we make mistake. Human makes mistakes. So what we can do is to limit to use what we learn, right, to limit the mistakes that we can do. So let's talk data representation. Representation. And let's start simple. A character, right? How do you represent a character? How should I represent a character? Anyone here familiar with ASCII? Anyone here familiar with ASCII? So basically, ASCII is a mapping between value and alphabet, right? Between a value and alphabet. So if you look at the ASCII table, right? If you look at the ASCII table, you will see that it goes from zero, from 0 to 255, which means that you need 1 byte to represent ASCII value, right? To represent ASCII value. And if I say my character is A, capital A, what's the value of A in ASCII format? So I have my ASCII table here to cheat, basically. But A is 65, B is 66. If I want to know what's the character for I don't know 103, you can look up at the table and I will see that's a letter lowercase g, right? So that's how you can represent alphabet using a string of binary, right? Because 65 is basically 64 plus 1, right? Which is basically this. Right? These sequence of binary 1 0 0 0 0 0 1 equals to letter A. 1 0 0 0 0 1 0 would equal to letter B. So this way you can convert from character to binary. How about string? A string, as we covered already in C, is an array of character, right? So each character is encoded in ASCII format. And how do I tell? Oh, Why do value of RGB goes up to 255 max? Great questions, because RGB is what? What does it represent? Well, it represents the intensity of the each color, right? Red, green, and blue. Red, green, and blue. So that when you want to show something on your screen, it shows the correct color. If you go and look at the color palette that the RGB can represent, it's actually kind of like really, really fine grain. You can have a combination of each RGB color to show the distinct color that you want. So it's kind of like basically with this format, we can do a good enough job at showing the correct color without burning too many bytes to represent them. So the intensity for the red would go from 0 to 255, green from 0 to 255, and blue again from 0 to 255. Right? So that's the intensity of the color. And the other thing, right? The other thing that's kind of nice is what's the material that is on your screen? Well, what is being used? I guess what's being used, the uh what is the material that are being used in your monitor? It's not it's the LED, right? LED lights, right? So these are LED lights that basically can do what? What can I do with the LED? The name stands for light emitting diode. Light emitting diode. It emits light, right? Exactly. The monitor would have the diode for each color. Then it would emit the intensity based on the number, right? So that you can get the mixture of the correct color, right? So when you have the LED monitor, basically it's a collection of these diodes that shows the color that you want. So now let's go back to the question of why RGB. Why RGB? You can use that number as the way to tell the diode, okay, go and produce the color at that intensity to get the correct color on your screen, right? Is it more clear when I explain it this way? Basically, it's a collection on your screen. It's a collection of diodes, and put you can basically control the diode based on the RGB value. So the R would go to the red diode. The the value for the G would go to the green ones, and the value for the B would go to the blue ones, and it would kind of together emit the color, right? And that's how you can actually display something on the screen. So is it more clear? Is it now way more confusing? I want to make sure it's not as confusing, or at least because we go side topic right now, like really really sidetracked. But it's a great question. All right, so I guess let's come back to the content of the class before we don't have enough time for the lecture. So the null value in a string representation, right? A null value would determine the end of string. For example, if I want to represent the string file pro, which is, by the way, historical point of view, this class used the name file processing back in the days, at least like 3 years ago. So if I want to represent this string, I can write FILEPRO and followed by the value 0. It would tell that that's the end of my string. How about integer, right? Integer can be represented using binary values, so that's pretty straightforward, right? And the size of your integer determine the maximum and minimum range for your integer. So if you look at NCC is like a textbook version of C. When you go and read textbook, they would pretty much most of the time refer to NCC, so that whenever you program, it's kind of the same environment. In this case, integer is 2 bytes, long integer is 4 bytes, long is 8 bytes. If you use GCC nowadays, integer is 4 bytes, for example, so that's the difference. Let's say integer is 2 bytes, right? I have to basically be able to represent positive number and negative number, right? For my integer. So what could be the range? The range that I can represent for the positive and negative number if my integer is 2 bytes. What could be the range of this number? So how many bits do we have in the 2 bytes data? How many bits do we have? Over here. 16 bits, not two. 16. All right, coffee. I think it's coffee time for you. So you have 16 bits. I need to represent the positive side of things and negative side of things. So what I can do is to break things in half, right? I will break things in half. I can start from -1, right, down to -2 to the 15, and +0 up to 2 to the 15 plus 1. My bad, -1. Sorry. 2 to the 15 minus 1. So this becomes the range of the number that you can represent. What will happen if you try to assign a number that are bigger than this range? So let's say I have a long j equal, I don't know, 1 million. Definitely bigger than that range. And I say int I equal j. What will happen? You are losing data. Basically, your data from this whatever numbers, I think it's 1 billion. Yeah, 1 billion would be truncate to something within this range that integer 2 byte integer can hold. Another thing you have to be careful about is the size of the data type can change across architecture and GCC version, even GCC version. So to me, I typically check with the command size off to make sure that you're working with the data size that you intended, because the consequence means you're gonna lose data or you're gonna have bugs on your code, right? Another thing is we have talked about positive and negative number. There's also another data type called unsigned. Anyone know what unsigned mean? So sign means I'm gonna cover positive and negative number. Unsigned means I'm just going to cover the positive, no negative number, right? So integer can be positive and negative. Unsigned means I'm gonna count only the positive number. So instead of having 0 to 2 to the 15 minus 1 and -1 to 2 to the 15, -2 to the 15, your number can range from, in this case, 0 to 2 to the 16 minus 1. the negative number becomes positive. For signed number, we use this technique, or the format actually is called 2's complement format. 2 complement format, what does it mean? It means that if I have, let's say my integer is 1 byte long, because I don't want to write something that's too long, right? Let's say it's 1 byte long and it's 10000010. If this is unsigned, this is basically 2 to the 7, right? Plus 2 to the 1. With me so far, basically, if this is an unsigned number, the value of this is 2 to the 7 plus 2 to the 1. If this is a signed number, you look at the most significant bit, which is this bit. If this bit, whatever this bit is, this bit becomes a negative value. So over here is negative 2 to the 7 plus everything else, this part is positive. But the 1 bit here is a negative number. So the value of this is 2 to the 1 plus negative 2 to the 7. So this is called the 2 complements format. The 2 complements format. We will talk about how to flip from positive to negative with the 2 complements format next week in the next lecture. For now, let's just understand the representation first. For constant value, in C, sign is just a number. So you can say int I equal -2. But for unsigned, you can explicitly say, hey, that's an unsigned number by adding the letter U toward the end. So what happens if you mix the two? Let's say you have an expression that has int I equal -2, int unsigned, int j equal 2, and then I want to do I plus j. What will happen? C and most programming language would treat both signed and unsigned that way, in a way that signed value casted to unsigned. Signed value get definitely in NCC, signed value is casted to unsigned. So to make sure things are safe, cast your data type when you have the mixture of signed and unsigned. Listen to the warning. The warning basically typically would tell you, hey, this thing might be wrong. So double check the data type. And now we will talk about why certain things exploded from the video we watched, right? When you do extension, let's say I have a 1 byte signed integer, 1 byte integer. So this is basically negative 128 plus 2, right? This is 126. I want to extend this integer from 8 bits to 9 bits. What do? Is I would extend by look at the most significant bit. If that's a 1, I'm going to keep appending 1, 1, 1, 1, 1, 1, 1 to the size we want to extend. If that's a 0, I'm going to basically extend with 0, 0, 0, 0, 0, so that the value doesn't change. So let's do this example. If I have this number, I want to extend 1 bit. I add 1 to them. And you will see that if this is a 9-bit signed integer, the value becomes the same. And we'll see how. Again, we go to the most significant bits, right? This is negative 2 to the 8 plus everything else is a positive number. Over here is a positive number. So that's plus 2 to the 7 plus 2 to the 1. And magically, this is minus 126, which is the same number. So you might be wondering why, right? Why is that the case? What is 2 to the 8? Negative 2 to the 8 basically equal to minus 2 to the 7 minus 2 to the 7, right? These are the same number, right? Because negative 2 to the 8 is negative 2 multiplied by 2 to the 7. So I can write it this way. The old 2 to the 7, flip the sign, right? So this part become plus 2 to the 7 plus 2 to the 2. So this thing cancel out. You're gonna end up with 2 to the 7 plus 2 to the 2 to the 1. 2 to the 1. That's why you can keep extending ones. So let's say I want to extend this 1 byte to a 2 byte integer. I would then add ones over here, and you ended up with the exact same value. You ended up with the exact same value. So what does this mean? Extension from smaller like int extend to a long int. It worked. The value stay the same. The value stay the same, right? So you can cast from int to long int. Truncation is a different story. Truncation is a totally different story. Truncation basically simply would drop n more significant bits, which means your value can change. Which means that your value can change. So for those of you during the break that watched the video together with me, the video is basically about the rocket launch Ariane 5. The test launch ended up with an explosion, right? So what happened is there's a certain data that measure the angle of the rocket relative to the ground, right? And somehow mid-launch, this rocket just go 90 degree. It's a go 90 degree. What happened is this number is represented using 64-bit floating point. 64-bit floating point. It get cast into 16-bit integer. Get cast into 16-bit integer. And why is that code not being used in the earlier version of the rocket, Ariane 4? What happened is Ariane 4 turns out there's hardware constraints, so this code was disabled. The code that is already buggy was disabled from the get-go. Ariane 5 turns out we have better hardware, so let's enabling this code. And the bug happens. It's actually way more complicated, right? It's actually multiple things going on at the same time. One, there's like a code that read the error in ADA that convert to 16-bit integer. And that's where the problem comes in, because you are basically casting 64-bit value, store that in the memory, and have the other program look at just the 16-bit integer. So you got the basically wrong results because there's not enough bits to store the value. End up in an explosion and loss of and basically a loss, right? So the summary of this is extension would yield the expected results, and truncation can change the value. And before we leave today, I'm gonna talk about how do we represent floating point number. So we have 3 pieces of information in the floating point number. And I'm gonna go with the 32-bit format. So this is the 32-bit 4 bytes format. Your data, ones and zero, will be grouped into 3 different parts. The first part, topmost, is a sign bit. It can be 0 or 1. If it's a 0, it's a positive number. These are not two complements format. These are just simple. If it's a 0, that's a 0. If it's a 1, that's a negative number. All right. Then there's a second part called the exponent bit. And the third part, that's called the mantissa bit. The 32-bit floating point means that the exponent would take 8 bits, and mantissa is 23 bits. So when you add everything together, one more sign bit, that's added up to 32 bits. Let E be the value when we convert this exponent bit. Basically, let's say the exponent bit is 1, 0, 0, 0, 0, 0, 0, 1. Then E is gonna equal to basically this number, 128 plus 1, which is 129. So we take care of the exponent. Let's do one thing at a time. Mantissa, the way you calculate it is, let M be 1 plus, this is basically 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, blah, 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 blah. The first bit right here in the mantissa bit, first bit right here, if it's a 1, it means you add 1/2. The next bit, if it's a 1, you mean you add 1/4. The next bit, if it's a 1, you add 1/8. The next bit, if it's a 1, you add 1/16. Then the value is this. Sign bit, we take care of that. You multiply by M, multiply by 2 to the E minus 127. 2 to the E minus 127. So let's go through this example. Here are the examples. How do I represent these values? 1.5, 1.25, 2.5, and 10. What is 1.5? 1.5 is 1 plus 1/2, right? This is everyone on the same page. 1.5 is 1 plus 1/2. 1 plus 1/2. So the floating point number, what should be in the sign bit? Yeah, 0. The exponent bit, we want to make sure that 2 to the E minus 127 equals 1. How do we specify the exponent bit? What should be E? 0, 1, 1, 1, 1, 1, 1, 1. That's 127, right? That's 127. It would basically make E 127. And when you substitute 2 to the E minus 127, you're going to get 2 to the 0. That's 1. And we want the mantissa to equal to 1 plus 1/2. And that's all, right? So in this case, our number should look like this. 0 for the sign bit. 0, 1, 1, 1, 1, 1, 1, 1 for the exponent bit. And the mantissa, the only thing we need is 1/2. So we have the 1/2 bit as 1, the rest are 0. How about 1.25? So this is 1.5. If I want 1.25, which is basically 1 plus 1/4, right? How do I change this so that I get 1.25? Sign bit the same, right? How about the exponent bit? Can I just use the same number for the exponent bit? Yeah, exactly. So 0, 1, 1, 1, 1, 1, 1, 1. How about the mantissa bit? I don't need 1/2. I need 1/4. I don't need 1/8. I don't need 1/16. Basically, the rest are all 0. So it's going to be 0, 1, a bunch of 0. How about 2.5? So let me change the color, my bad. Let me change it to blue. 2.5 is going to equal 1.25 multiplied by 2, right? So one thing I can do is what? I can keep the mantissa bit. to be 0, 1, 0, 0, 0, 0, 0. But I want to multiply by 2. How do I change the exponent bit? So from e equals 127, in this case, you want to multiply by 2 to the 1. So in this case, e should be 128. Right? So e should be not exactly this. It's e minus 127, so you need to plus 1. Add 1 to e. So it's going to be 1, 0, 0, 0. All right. How about 10? It's okay. It's okay. It's late in the afternoon. That's why I also give everyone a lot of time on the exam, right? Make sure you clear, like, have a clear, and really high on caffeine, making sure you are fresh to the exam. 10 is basically 1.25 multiplied by 8, right? So again, I can keep the same mantissa bit, 1, 0. Same sign bit. But then I want e to be what? I want e to basically result into 2 to the e minus 127 such that is 2 to the 3. So e minus 127 equal 3. E is going to equal to 130. 130 is 128 plus 2, so it's 1000. And that's all, right? So this is how you can manipulate the floating point number. This is how you can manipulate the floating point number. In the next lecture, we will talk about operation in binary. I want to wrap up the lecture today because there's quite a lot more things to cover before we kind of wrap the data representation. So for now, we switch over to Discord, spend the last 10 minutes on Q&A for both in class 7, 8, as well as assignment 2. All right. So I'm gonna basically, first of all, I'm stop the recording and I'll